Okay, thank you, Milan, for the introduction. Yeah, it's about the PowerBoard Visualizer GUI that has been developed for a certain amount of time, and now we are in the stage where we think it has enough features and stability to use it in wider range within microchip. So I have this presentation structured in 3 parts. Shortly, something about the serial communication protocol, a little bit something about the source code, and then the live GUI demonstration itself. I hope we have a little bit more time than 15 minutes. So yeah. About the serial communication protocol, we have standard serial interface UART between our devices and the PC. So far we always used it with USB, serial over USB. As I understood, also from information from France, there is a serial communication protocol that is already being used from many people over many years within microchip, and the serial communication between the embedded device and the PC is based on that. So depending on the protocol ID, the data that is inside these packages then means something different. We use it to send multiple values to the GUI. So like voltages, different kind of ADC values or status bits and so on. Also for receiving data back from the GUI. So if the GUI wants to change the voltage reference, for example, or it wants to trigger an event to start something, these are the data packages that are coming back from the GUI to the embedded device. And also we added a scope function so that we can investigate or also demonstrate some high-speed signals. So where on the embedded device there is a record triggered, and this then fills a buffer of samples and sends it to the GUI. Also, we can trigger such an event from the GUI. That's a little bit of a delay, but yeah, this trigger command can also be embedded into the source code. We used it, for example, in the 4-switch buck boost in the startup. So then we can nicely see some kind of voltages or currents in the startup phase. So the structure of the source code is not very complicated. It is based on the MCC. So what we practically need is a UART interface of the MCC, and this is where the def GUI com layer comes in. This is our communication layer that does all this protocol stuff. In our project, we also have our scheduler, operating system scheduler inside that allows us to call a lot of functions and parts of the software with different timings, and comes with some standard timings that we use for a lot of applications. Yeah, in our demo also there is an ADC driver, LED driver, button driver. LED driver or button driver sounds a little bit over the top because what do you do? Just switch on or off some pin or read out some state of a button. But these drivers also can do a little bit more. They are connected to the timing of the scheduler, so the LED can blink. And you have very nice interface functions for slow blinking, fast blinking. Also, the button driver has nice features for getting an information if the button is longer pressed and has a debouncing algorithm inside and so on. And above this, you can see the HMI and the GUI app. So the GUI app is the part that communicates with the PowerBoard Visualizer GUI, and the HME application is the application-specific implementation for buttons or whatever the application should do. Yeah. So here we have a little bit of an overview. So the Def GUI COM layer can be used as it is. It is not CPU or MCU specific, so it does not contain any commands for handling this CPU direct. So you can use this source code and also then try to use it in 8-bit applications or other 32-bit applications. We haven't tested this so far, but it's CPU independent because it connects to the MCC UART driver. But you can also use your own serial interface drivers. And here in the H file, in the include file of the GUI COM layer, you can define the functions for your specific UART. And with this, it should work fine. So a little bit of the functions that come with this GUI COM layer. So we have this stream of data that is constantly, repeatedly sent it to the GUI. That contains, things like I mentioned, voltages, currents, some ADC values, and maybe also some statuses of a state machine or something. And we have these three functions so that we can see if we can start now a send. Then we have these send word commands to send the individual values, and after that we say finish sending, and then this package will be sent automatically from this GUI layer. For receiving data, we can have our own application-specific handler. So this is the function that handles the incoming data from the GUI, and with this function you can register this protocol handler so that it gets called when some incoming data is coming in from the GUI. So an example of this, here we have a task that is called every millisecond. This is the app GUI task, and it's practically asking if the GUI layer is ready for sending something. And when the GUI layer says, yes, we are ready to send something, then these send word commands are being called. And with these commands, you can send your data to the GUI, whatever you want to send. And after this, you say, I'm finished. And you can update only 2 values, or you can update all the values that you need. That's up to you.
Stefan, one question about the send word. Will this wait until the bytes are sent, or are the bytes buffered somewhere and then sent by interrupt?
Yes, these are buffered. So the GUI COM layer contains a small buffer for these words, and it starts sending when this finish sending command is being called.
Okay, understood. On the other hand, this means you need sufficient RAM for all send words you put in this routine.
Yes, that is right. So there's a small buffer required for holding this data and for sending. Yes. And when this package is being sent, then this buffer can be reused again. That's hidden in the GUI layer there, in the GUI COM layer, and then you can fill in the next values again here. Yeah. So this is for sending. So very simple for your application to constantly send some values. And receiving, of course, is also possible. So I have now in the demo source code 2 data packets that I am sending from the GUI back to the embedded device. And for these data packets, I defined a command. So I defined a command for setting voltage, for reference voltage, for example, and a command for changing the LED status. So, and in the init function, I just register this protocol handler with the protocol ID 0002. And then when some incoming data is coming, this function is automatically being called. And in this function, in this application specific function, I can then look what is in this data. And in this case, we have the command in the first byte. And depending on the first byte, we then, for example, call changing the red LED mode. For voltage, we would then look at the other data bytes and extract the new voltage, for example, voltage reference. So then we have scope functions. So this is more for real-time things. So in this case, we have a task function that is being called every 100 microsecond. But it can also be called faster in the four-switch buck boost. I think we have a frequency of 250 kilohertz or something that is getting triggered from the ADC interrupt, and there we use this function, the GUICOM scope record function, and we just put in here 2 values. And these values are also recorded in a buffer, and you can adjust the size of the buffer. And so you can say, okay, 100 values is enough. In our code example, we have a lot of RAM left, so we use 1000 samples, which then we can see later. Yeah. And to trigger this recording, we have to use this command, trigger now, and then this function records the samples in the buffer. And when the buffer is full, it automatically transfers it to the GUI. So you practically just need these two functions in your application, then you have a scope functionality in your application. So let's go to the real deal here. I will start the software, and I will start from scratch. So we got the last version yesterday, and I tested it, and all these functions should work now nicely. Project name, no. PowerBoard demo. So we use usually 115 kilobaud for our serial interface. And now we have to specify some signal channels. These are the individual values that are getting sent to the GUI from the software. And I add simply a signal channel. The first is B and C input. Scaling. So I'm sending here ADC values. So the exact values that are coming out of the ADC conversion. And we can do here a scaling in the software so that we then have millivolts. So maximum value, I don't know exactly, but yeah, 1000 millivolts. So this is the first byte that is transmitted in our message. And so its position is in message is 0. So now we have this value here inside. I add quick some other values. So on our power board, development board, we have a potentiometer, 2 potentiometers, and we can visualize the state of the potentiometer. The minimum and maximum plot values, they are important for the scaling in the monitoring diagram that we can see later. So now we have defined our signal channels, and now we can make a table here to display all these signals. So I will display them all here. So, and what I'm doing now is I'm configuring the serial interface and enabling it. And with this symbol here, blinking red and green, you can see that there is some data already coming in. And when you look in the table up, then you see, yeah, there is something coming in already. So that works nicely. Now we can add a status group for our LED. So we have an LED on the board, and this LED can have different statuses, and with the button on the board we can switch from different statuses, and one is, for example, LED off, that's bit 0 of this status word. Then we add LED on, bit 1. We make it look like a radio button because it's a group that should be grouped together. So then LED normal. And the last one, LED blink fast. So if I push the button on the board now, then you can see already the LED status in the table and also here as a bit being updated. So to demonstrate that we can also control our application, our board, I can add a button here that says switch LED status. Enable this button. And now we need to know the data that is going to the board. The first is the protocol ID. So protocol ID is 0002. This next one is the length. So it's only 1 byte long, and it's the byte 02, which says switched LED status. And when we click on it, I hope it works. Yes. So now you can see that we can control, yeah, our embedded device with this. Then I can also add a slider. I call it voltage reference, unit, volt, scaling 10, minimum value, let's say, yeah, 0, maximum value 15 volts, step 0.5. Do we have it? Okay. Yes. So now I want to transmit this voltage reference value to our board. So we have to fill out the values here. Let's say update value. And then I need also this data bytes that need to be sent. So in this case, I have protocol ID 02. Then I have the length. Then I have the command. So the length is 3 bytes. Command is 01, and then I have the value of the slider. So now I have a button. I can adjust to some voltage, and I update the value. Okay, you can see it already here. I have a scaling of 10, so 8.5 times 10 is then 85, and this value of 85 is transmitted to the board, and the board sends it back here in our demo software as this value here. But also we can edit it in a way so that this is being sent automatically when we change the slider, and you see it on the left side that it is very fast, and the board already transmits the value back. So these are practically the things on this page that we have here. Let's save it. So we can save our configuration. So in case it crashes, I hope not, but yeah. Then we have a tab here, which is called schematic diagram. Schematic diagram, we can add a schematic diagram. And this is a graphic that we can add. So in this case, we don't have a real schematic diagram. We have just the pictures here of our development board, and also the PIM here. Here you can see the numbers to order it, the product number. Yeah, and now we have a very nice feature. We can add some signals here. So I say add point, and then I select this is the BNC input. And now we can see, just move it a little bit. Now we can see this is the input signal that we also see here in the table. And for the pot value, I also add potentiometer 2. Yes. So if I change the potentiometer, you see the value going down. And if I turn it up, it goes up. So very nice live feature. Here on the right upper side, we have the LED status. So yes, when I press the user button on the board, you can see the actual LED status that we have. Yeah, then we have the user guide section. So we can also add a user guide. It's just a PDF. So we add a PDF here, and there it is. Then we have the info tab. This is in HTML format. This is where we usually have our protocol inside. A protocol description of the layers. So now we have a lot of stuff here. I think that's everything that we now can configure. And now I can show the monitoring. So I want to monitor, for example, these three values. Then I go here to the monitoring tab, and we can already see them. The blue line up here, that is the potentiometer status. So I can change the potentiometer, and you see the live update. I hope this works good through Teams, fast enough that you can see something.
It does.
At least for me, it looks
Yes.
good.
Yeah, wonderful. Also when I push the button, remember this changes the LED status. So you can see here 0, 1, 2, 4, 8, 16. Yeah. So these are the values that we constantly sending. This is not very fast. I think we have here about 10 values per second or something, but this is enough for the usual recording of stuff. But of course, very interesting for high frequency stuff, for real-time recording then, is this scope graph, this scope function. And there I have the possibility to add some buttons here that that send a small data stream to the board, and then the source code on the board does something with it. And in our case, we have already something in this GUI layer inside, and this is the trigger function. The trigger function, and I hope I get it right now. Okay, that's not the name. That's data. So I say trigger now. So now you can see this button here, and when I press the button, yes. So it sends this small data stream, these few bytes to the board, and in this GUI COM layer, we already have this code that starts then this trigger now function. And do I have something else here? Recall. So try it again. Okay. So now you also see these records that I made. So I can switch between them, and then I already also compare different scenarios. So this is also very nice to demonstrate some things to the customer, but it is also helpful for a little bit of product development for us. So startup scenario of our power conversion things. We can have some voltages or some internal calculations, for example, visualized here. Because with the real digital oscilloscopes that we all used to, we can only measure some external signals that are coming out of the microcontroller. Franz, as I understood, sometimes use an extra pin of the microcontroller to visualize some internal value and put it on a DAC output, and uses his microscope to visualize what's going on inside. But here, you can also transmit some other values like internal calculations, and then you see if there is an overshooting or overrun of value and such stuff, and you can then put it here in the scope. So that's also very helpful for development. But yeah, for demonstrating a little bit high frequency real-time stuff for the customer without having to carry around an oscilloscope and stuff, this is also very helpful. So for the people who are in the field talking directly with customers, they just use the demo boards and the software on the PC, and you don't need to carry around a lot of other equipment. So, okay, I think we are finished with this.